Good afternoon, everyone, and welcome to the Quantum Webinar Series featuring Dr. Bruno Abreu on the topic of pathways to hybrid quantum and high-performance computing. I'm Farouk Garamani, Vice President for Research and Innovation at New Jersey Edge. The Quantum Webinar Series is a partnership between the Ecosystem for Research Networking, ERN, and the Northeast Big Data Innovation Hub, NEBDHub, and brings together leading researchers, students, industry experts, and innovators to explore the latest breakthroughs in quantum science and technology. I want to bring your attention to the Code of Conduct. The Northeast Big Data Innovation Hub provides a supportive and welcoming environment to everyone. The hub promotes a safe environment free from any type of discrimination or harassment. Our hosts and moderators for today are Florence Hudson, who's Executive Director of the Northeast Big Data Innovation Hub, also the National Student Data Corps founder, as well as at the Data Science Institute at Columbia University. And Florence is also on the ERN Steering Committee. Emily Rothenberg, who's Program Manager at the National Student Data Corps, Northeast Big Data Innovation Hub, Data Science Institute at Columbia University. And myself, I'm also on the Northeast Big Data Innovation Hub Steering Committee and the ERN Steering Committee. And we'd like to welcome Dr. Bruno Abreu, who is the Deputy Scientific Director at the Pittsburgh Supercomputing Carnegie Mellon University, where he leads quantum computing research and systems design. Please join me in welcoming Dr. Abreu.
All right. Thanks everyone for joining today. Let me start sharing my screen here. And thanks all the organizers here who kindly invited me and all the support that you guys put into this. It's great. I just have to come and give the talk. So you guys did all the hard job, the hard work. So what I have today here, Farouk mentioned that my background is there was a blurb about my background. I am a quantum physicist by training, but over the last several years, I've been working on the high performance computing sort of community and environment. So what I want to do today is really give you a way to think about quantum computers and quantum technologies in general as computing resources, as scientific computing resources. Um, I don't want to teach you physics here. That's not the purpose of this talk, but I do have to go into basic concepts that to make sure that everybody's on the same page. So if you already know quantum physics, bear with me for a little while here. The second half of the talk, we're going to get more into hybrid workloads and applications, and more into how these quantum machines basically should be integrated or can be integrated into the whole traditional non-quantum infrastructure that is extremely advanced these days and that has enabled so much science and engineering, discovery, innovation, so on and so forth. So I'm gonna try to find a chat here. Oh, here it is. Yeah, so please feel free to drop questions in the chat. I have stopping points that I'm gonna try to use and keep an eye on the chat here. But if there's a question that I don't address, we'll have some time in the end for you to answer for you to ask again. So I have an outline here. It's kind of a menu. I call it a menu because usually what I do is like I select parts of this depending on the interest. So I'm gonna go over my normal pace here, but if there's something that I'm seeing more questions in the chat, like we can spend more time in each one of these sessions depending on your interests. So we're going to talk about basic quantum information science concepts, how we do quantum computation, some examples of quantum algorithms, then go into quantum applications, and then we're finally going to dive into the infrastructure for that. High level vision of quantum computers and how quantum supercomputers can be built. All right. Let's get started here with some really basic concepts. Quantum objects in general, particles or systems of particles, what it's interesting about them is that they have this dual nature, this duality nature. They can behave as particles or waves depending on how we interact with them. So when they behave as particles, really means that their dynamics, the way they evolve in time, it's characterized by a specific trajectory. So it goes from point A to point B, and we can define where they are at a certain time. When they behave like waves, this is a little different or quite different. You don't know exactly what the trajectory is. What you know is a sort of a probability of where to find that particle or in what state to find that system at a certain point in time. So the dynamics here in when they display their wave behavior is really characterized by these probability amplitudes. What's funny here, or maybe it's just not funny, but it's interesting that the electron, a fundamental particle, was discovered as a particle by J.J. Thomson in 1897, and then 30 years after, his son, J.P. Thomson, demonstrated that the electron behaves like a wave. So the father said that the electron is a particle. The son said that the electron is a wave. They both got Nobel Prizes. The other concept that is relevant for us here is the concept of superposition. So if the particles are interacting like waves, they can be in this sort of state that is called a superposition, right? So think about a particle trapped in a box, right? So the particle can only be in between this space here. There are walls to the left and to the right. Um, Typically, what happens is that there's a lowest energy state that this particle can be. This is called the ground state. And then this ground state represented by this symbol here, you don't have to know what the symbol is. It's a cat, not a cat animal, but it's KET. So in this lowest energy state, the probability amplitude is like this. So you can't find a particle on either side of the box in 0 and L here. There's a 0 probability amplitude for me to find a particle there. So the most of the probability, the density is actually here in the middle of the box, which means that you're more likely to find the particle in the middle of the box. For higher energy states that are not necessarily the lowest energy states, this changes, right? So like the first excited state of this system here with one particle, actually, if you look at this, the probability amplitude has a node here. So that means in the first excited state, I have 0 probability of finding the particle in the middle of the box. And I have some probability of finding the particle at the first third of the box and the second third of the box. Superposition means that I can prepare particle states in a combination of these different states here. So if I combine the ground state with the first excited state, what I get is this even more interesting state here where there is a node. I cannot find a particle here, and then what's also more interesting in this is that there's a higher probability of me finding the particle to the left than there is than the probability of me finding the particle to the right. So I can combine these different different modes, we call them modes, into superposition, and then it can create states that are a combination of modes. And if this sounds all confusing, it really isn't. This is just waves. If you ever played an instrument, that is exactly how chords work. The last sort of a element of quantum information science that we need to use for quantum computation is entanglement. This one is a little bit more subtle, right? So when you have multiple particles, just before I was talking about just one single particle. When we have multiple particles, we need to find a way to describe the joint state of the system, right? The state of these two particles together. Suppose that these two particles do not interact. They don't have any interactions. They are independent, right? So the particle to the left, the blue, I'm going to describe that, say that that particle is in a superposition of those two states that I just showed you. It doesn't matter what they are. It's just a superposition. And the red particle is in the same superposition. If they're not interacting, what happens is that the state of the system, the two particles, is described by the product of the joint product of these two specific states. So particle blue product particle red. If you do the math here, you're going to see that this is how it plays out, right? So there is a mode where particle blue is in the zero state, particle red is in the zero state, and there's a mode where particle blue is in the zero state, particle red is in the one state, and so on and so forth, right? So without interaction, the joint state is always the product of the individual states. Now, if we add interaction, things get a little different. So with the interaction, I actually can create states that do not correspond as a specific product of individual states. So there's a state here of the joint system 0, 0 plus 1, 1. You cannot write this state as a product of individual states. There's no way. You can try as long as you want. So that means that these particles are correlated in a way that classical mechanics, classical physics is not able to describe. They have correlations that are inherently quantum and that rely on this some of the underlying basic principles of quantum mechanics, Heisenberg's principles, and so on and so forth. So that's entanglement at a very, very, very high level. Now, how do we use these things, right, to process information? So I think as computers in general, not quantum computers or classical computers, just computers in general, as information processing machines, right? So in the classical or conventional case, computers basically use two resources. They use memory and they use processing power, non-quantum information processing power. So you can think about a computational space for conventional computers as a two-dimensional space. It has a space in a side, physical space in the sides in one direction and time in the other. And what a conventional workload, you're doing a molecular dynamics simulation, whatever that is. A conventional workload is really just a path in this computational space. It brings you from point A to point B. Okay, so memory fluctuates with the memory you're using fluctuates as you're computing more things, and the time passes, and the more processing power you have, the faster that time passes, right? So when we bring quantum information in, what really this means is that we have extra dimensions to do computational now. We can leverage those two phenomena, those two concepts of superposition and entanglement to do computation over that extra dimension now. So hybrid workloads that we're going to be talking about are really just another path in this computational space, but they explore this extra dimension here of superposition and entanglement. The question, though, is that computing on this extra dimension here can be expensive. Leveraging these resources here, superposition and entanglement, can be expensive from a resource perspective. The way I like thinking about it is that we have different ways to get around. We can walk, we have bicycles, we have cars, we have helicopters, right? So helicopters are extremely useful for certain things, but you're not going to use a helicopter to go to the grocery store, right? So this is really kind of the same thing here. You have this extra dimension here, but you're really only going to use it for specific use cases, right? So a helicopter is extremely valuable for a hospital, for instance. But again, you're not going to use it to go to the grocery store. You can use your bicycle, you can walk, you can use a car. So really, what the art of thinking about hybrid computing is thinking about the problems where going to this extra dimension here is actually going to help you. So that is like quantum information science in a nutshell, like, as quick as I can give you an overview of that. So using these concepts, how do we do computation? What are the basic elements for you to do computation using quantum information science elements, right? The first one is the unit that's going to hold the information. In conventional computing, this is the bit, right? Bit is something that can be in a 0 or 1 state. You add a lot of those together, you have a computer. For classical information, the fundamental unit is a qubit or a quantum bit. Basically, in terms of quantum mechanics is a two-system level. It's a system that can only be in or can have two different quantum states. And of course, you can have superposition between those states. So the superposition here is basically generically described by two numbers. These numbers are complex. They're not real necessarily real numbers. So because of that, the space that you describe, the space that you use to describe the state of a single qubit generically, you can kind of map it into a sphere. The north, or not kind of, you can exactly map that into a sphere. So the north pole of the sphere is the zero state. The south pole of the sphere is the one state. And anything else in between, you can map to the surface of this sphere. The way we build qubits, there are many ways to build qubits, and that's we're going to talk later about quantum computing modalities. But basically, you can use different physical systems, physical support mechanisms to build qubits. For instance, you can use a photon, which is a particle of light, and then you can use the polarization of that photon to represent the two states of your qubit. You can also use an electron, and then you can use the spin of the electron to represent your 0 and 1 states. You can use a Joseph junction, doesn't matter what that is, but it's another physical support that you can use to build qubits. There are many of those out there. This is an active research field, and people at this point, they're not only discovering other ways to do physical support, but they're improving the functionality of these qubits or the reliability of these qubits, depending on the systems that they use. The next element of this, okay, yeah, I have a qubit that's a unit of quantum information, that's a unit that can hold quantum information, but how do I manipulate that? In the case of classical bits, you use logical gates, AND gates, OR gates, XOR gates, you name it, right? There are a lot of them. For quantum information, we use quantum gates. It's basically the same thing. What a quantum gate does is it brings a certain quantum state, a certain qubit state, to another one. So here are examples. I'm bringing a certain psi state into a new state by applying a Y gate. Doesn't matter what a Y gate is. Here's an X gate, and you can also use two qubit gates. So gates that are acting in two qubits at the same time. So that's how you manipulate them. For example, we talked about superposition between 0 and 1 before. There's a specific gate that creates that superposition. It's called a Hadamard gate. So the way I create a superposition from for going from the zero state to a superposition of 0 and 1 is by applying this Hadamard gate. So the representation of the block sphere that I just showed you in the previous slide is okay. So initially I'm in the zero state here, so I'm pointing to the north of the block sphere. Then I apply this H gate, and now I'm in the superposition of 0 and 1. So I'm not in the north anymore. I'm actually pointing towards the x-axis here. So this is really how we manipulate the states of the qubits. Of course, as I mentioned before, to create entanglement, you need basically interaction, right? So you need gates that act in more than a single qubit. So some of the the most common gates for two or more qubits are the C0 gates or control NOT gates, and the Toffoli gate that act in 3 qubits. Back to that story about the helicopter and how hard it is for you to actually use that extra dimension. Gates that involve many qubits are more difficult to apply. So we're going to get to that later when we talk about quantum computers. When you combine all these qubits and all these gates to describe how you do computation, you have what we call quantum circuits. So this is really how you do operations in a computational space with many qubits, right? So here's one example of what a quantum circuit looks like. There's some elements here that I'm going to point you to. So a qubit, the sequence of gates that act in a certain qubit is really represented on top of what it's called a wire. These are the qubits right here. You can see at the bottom here, there's a little C here because we're talking about hybrid computing. There's no such thing as purely quantum computing. Okay, you always need classical support. You always need at least a minimally working conventional computer by your quantum computer to do anything. So you can have classical bits also holding classical information. So for instance, I have like several Hadamard gates applied to these different qubits. Then I have C0 gates here and so on and so forth. And you can see that this black one here is actually a measure gate when I go and measure the state of the qubit. And I didn't talk about this on the QS, the quantum information science core concepts, but there's this thing that when you actually measure the state of a qubit, you're never going to find a superposition. You're going to find either 0 or 1 with different probabilities, but it's either 1 when you measure. So when you measure, you can actually map that back and store that information into a classical bit. So this is basically how some sort of quantum computation, it doesn't matter exactly what this does. It's just building another quantum state and then measuring that in the end. Um, Other elements of this is the circuit width and the circuit depth. So people refer to these a lot. A wide circuit is a circuit that has a lot of qubits, and a deep circuit is a circuit that has a lot of gates applied to these qubits, right? So those are the two dimensions of the circuit. These three things, qubits, gates, and circuits, are really how we do quantum computation using quantum information. Here's one example. We talked about entanglement, right? So how do I create an entangled state? There's this thing called a Bell pair, which is basically a two qubit state that is maximally entangled. That's the maximum amount of entanglement that you can put in a certain quantum state with two particles. So sorry, went ahead here. So I'm representing the state of the system by the joint state of qubit 0 and qubit 1 here. So if I look here in the first stage, usually what happens is that qubits are initialized in the 0 state. So what's happening here is that at this box here, this first box here, I have a 0, 0 state. Now I'm applying a Hadamard gate in the 0 qubit on top of this initial state here. So I'm applying the Hadamard gate on the 0 qubit on the initial state here, 0, 0. So what the Hadamard gate does on qubit 0 is putting qubit 0 on a superposition of states. So I have 0 on the qubit 1, and then I have a superposition of 0 and 1 on qubit 2 on qubit 0. Then I use a C0, and what the C0 gate does, it's basically hiding, I'm hiding the math here, but it's basically creating that state that I told you before that cannot be written as a product of the independent states. So this is basically how they operate. You can always map a circuit back into operations of the gates on your quantum states, right? So and you can do that in classical computing as well. So those are the elements for quantum computation. We talked about core elements of information science, how we use those core concepts to do quantum computation, and then we added these elements of how to do quantum computation, right? So, okay, that's great. Thanks, Bruno, for showing me how to build a Bell pair, but what the heck do I do with it, right? So what are things that we can do that have practical purpose, that help us do scientific calculations, basically? So let's talk a little bit about algorithms. Let me check on time here to make sure that I don't go too far on time. So there are a few algorithms that have been around for a long time, and the reason why they're so important is that they are the ones that, remember, we talked about when you go to the extra dimension, that can be expensive, and you really want to find the problems that make sense, that it makes sense for a hospital to have a helicopter. So these algorithms are exactly that. They are the algorithms that really show advantage when I go to that extra dimension, when I explore entanglement and superposition. So what Grover's algorithm does is that it runs a search in fewer steps than any classical algorithm that you can possibly find. So if you want to define this problem a little more in a more rigorous fashion, you have some sort of function that accepts items. If the item is a solution to the search task, then the function returns 0, otherwise it returns 1, otherwise it returns 0. The problem is find any item Z such that the function returns 1. So basically, you have a list of objects, of items. and you want to know if a certain item that you bring in is in the list, is on the list or not. What type of actual problems this translates into? Traveling salesman, what's the shortest loop connecting all cities for someone who's traveling over all of them? Database searches, if I have a table and I have some record, does this record is this record in the table or not? And Boolean satisfiability in general. Does a certain set satisfies a Boolean formula? This is more like the mathematical problem associated to it. So I'm obviously not going to go over all the details here, but what you can show is that classical algorithms will, depending on the size of your search space, the size of your list of objects, classical algorithms can basically perform this search in a way that increases linearly in a number of steps that increases linearly with the size of your list. What Grover's algorithm does is that it can actually do the search with the square root of the size of the list. So you're getting a speed up here. This algorithm, as your list increases in size, Grover's algorithm is increasingly faster than the actual classical algorithm. So you're leveraging superposition and entanglement to achieve what we call quadratic speed, because there's this one's square root, the other one is linear, so there's a quadratic speed up there. Um, so here's one example of how Grover's search would look like using a circuit for a very, very small problem, right? This gets really, really big. This circuit gets huge as the space the problem space here increases. That's very simple. I can't even remember how many items you have in the list here. It might be only two. So that's one of the examples where you have quantum speed up. The other one that is very famous is Shor's algorithm. You probably heard about. And what Shor's algorithm does is does factorization in fewer steps than in a classical algorithm. What's factorization? Basically, if you have a composite number, you need to find what are the composing the sub numbers that compose that. So what are their integer factors? Applications for that: public key cryptography and finding the period of a function. Again, what happens with Shor's algorithm is that it beats the best known, and probably these are old problems. So if people haven't found a better classical algorithm by now, they probably won't ever. So it beats the classical algorithm depending on the size of the number here. Like at a certain point, depending on the size of the number that you have, um, there's a crossover between Shor's algorithm and classical algorithm. So Shor's algorithm starts to become faster than the classical algorithm. This is called polynomial speedup. Here's what a Shor's algorithm circuit looks like for a very, very small number. I think this is a 4-bit number, maybe. Can't remember, but it's a very small number. You can see that the circuit gets increasingly complex. You have a lot of one gate circuits here, but then you start having one, two, three, four, 5 gate operations here that are pretty complicated. And in the end, there's a quantum Fourier transform here that actually acts on all the qubits at once. So it gets increasingly complex with depending on the type of algorithm that your circuit gets more and more complicated as your algorithms get more complex. The other one the other type of algorithm that can show quantum advantage in the short term, right? Grover's and Shor's algorithm they require advanced quantum computers. We'll get into that later. Um, myself as a physicist, I'm really excited about using quantum resources and quantum computers to study quantum systems. And then as we talked before, what really matters is not doing only quantum computation, is doing this hybrid computation where you're also using classical information processing while you're doing quantum computation. So an example of that is what we call variational eigensolvers. So the problem here is finding if you're a chemist or if you're a physicist, this is obvious. Find the ground state of a system with Hamiltonian H. That means that I have a way to describe my system. I know what the interactions are. I know a certain initial state. and I have to solve the dynamics of the system. I have to solve in a classical case that would be equivalent to solving Newton's equations. In a quantum state is equivalent to solving Schrodinger's equation. And then I want to find what's the ground state, what's the lowest energy state of the system. That's a very important problem in several areas. That's how people do electronic structure calculations. This is very important in high energy physics and condensed matter physics and optimization in general, because it can usually translate well-defined cost functions into a Hamiltonian type of problem. I have a question in the chat. How do you account for information noise or quantum error correction? I have slides about that in a few minutes. We'll talk about it.
I do have a question, another question.
Yes, go ahead.
Yeah, my name is Atish. Uh, about these algorithms, if we can you please shed some light on if we don't have a quantum computer, a reasonable quantum computer at the moment, how do we know or how do we estimate the time complexity of these algorithms like Grover's, which is square root of n, or Shor's algorithm,
Yeah.
or any other algorithm? How exactly do we do that? We can't really imagine this, right?
Yeah, sure. Thanks for your question. So the reason why Shor's algorithm and Grover's algorithm are so um, prevalent is because there are rigorous mathematical proofs that that's how they scale, right? Your question gets more interesting because there are other quantum algorithms for which the mathematical proof of their speedups it's not well defined. For those, that's an active area of research. Um, then you need to actually run those things in a quantum resource to know that they actually bring some sort of advantage. So there are only a few algorithms, Grover's and Shor's are examples, where you know that you get speed up. That's mathematically proved. For several others, some of them we're going to talk about maybe later. There's no mathematical proof, and then you have to rely on basically a scaling experiment on a quantum resource. So that's an active area of research.
Got it. Thank you.
Sure. Okay, so back to the eigensolvers here. This problem is really important. It goes not only into physics, chemistry, but it goes over optimization. There's a lot of stuff that happens, that a lot of actual practical applications that translate into this type of problem. This is an example of a hybrid algorithm because it involves quantum classical resources, right? So the way this works is basically I prepare my state and then I parameterize a circuit. So now I have parameters that I can play with. And then this, when I measure everything here, when I measure all the states of my qubits, I can estimate a cost function associated to how far am I from the actual ground state. And then with this cost function, I can update my parameters. You can think about gradient descent. It's basically the same thing that people do with neural networks. So I can update on my parameters and do this over and over again until I find the state with the lowest energy. So it's really about updating these parameters, calculating the energy expected value of this Hamiltonian until I minimize that. Do that over and over again. Here's one example of this process actually running. Here's the number of iterations. This is the energy. This is an example of a two-site Bose-Hubbard model. If you know what that is. If you don't, doesn't matter. But you start with a high energy here, and you can see the red line here is the actual solution that we know for this particular case. But you can see that as I run the algorithm, it approaches that solution. So it really is going to find the lowest energy state. Those are example of algorithms. Okay, there are others. Quantum algorithms. It's an extremely active field now. If you look at the archive, look online, there are papers everywhere about these things, right? So I'm just giving you a very high level view of what these things are. Okay, great. We know basic information science concepts. We know how to do computation. We know some of the algorithms. What can we do with this? What type of applications can we do? And I'm going to run very high level here quickly over the applications because I want to get into the quantum computers and quantum supercomputers. That's really what I want to show you today. Examples of applications are real, they're everywhere too, but I'm going to pick two here. Basically, drug and material discovery. Why is this important? Is because chemistry and physics, they all of these materials and drugs, they are quantum systems, right? So you need quantum mechanics to represent to analyze those systems, to actually describe those systems. Um, so without a quantum resource, there's only a few ways. Either a problem is too big to fit in any classical computer, so you have a size problem. And if you have a size problem, what you usually do is that you don't do fully quantum treatment, you do approximation. So then you have an accuracy problem. Um, the other part of this is that if you use quantum calculations, you can actually expand and make better AI data sets. We can talk about that later if you're curious of what that means. But here's the typical workflow if you're doing drug discovery, material discovery. There's a paper here that you can refer to. But you do some sort of experimental structure determination. You do some sort of initial classical pre-processing to kind of refine that structure. You do some sort of algorithm design, whether it's going to be variational eigensolver or other types of solvers. And then you finally do your quantum computation. You prepare your state, you run the algorithms, you analyze the properties. Does that match the property that you wanted? You run the cycle over and over again, right? So that's typically how this works. Uh, the other one is the other type of application is really logistics and optimization, right? So it's like you're trying to solve an optimization problem. You're trying to figure out how to do a supply chain type of problem. Um, that's another thing that involves quantum and classical computer. We saw an example before of us updating the parameters in the that requires a classical computer. So you input your problem here, you compile this in some sort of efficient representation using things like, these are technical quantum computing terms. You can make better gates. We'll talk about noise in a little bit. Um, but in the end, you have some sort of hybrid quantum classical execution here. So your quantum hardware is working with a classical computer to output a solution here. In this case, um, this case, it's doing some sort of what is it called? Binary optimization here. It's a paper that by IBM, by the IBM team that a couple of years ago was very, very impactful. In terms of like broadly, what type of domains are actually seeing these things? Here are some examples. Banking, healthcare, electronics, telecom, energy, oil and gas, chemicals, insurance. I have some papers here that you can look for more specifics of the examples, but basically what I want to point out to you here is that um, there's a common thread between all these applications here, which is these are industries that move and generate a lot of money. So this means that for certain players in these industries, squeezing a little margin of advantage translates into millions and billions of dollars, right? So any speed up, any advantage that these folks can use that can find is gonna kind of like give them this edge against their competitors. You're not seeing many of the actual sort of more scientific, academic, scientific problems using quantum computers yet, because for a typical scientist, getting a 1 or 2% speed up on their computation doesn't really matter, right? If I have something that runs for 2 days and now it runs for 2 days and 5 minutes, so what? For some academic cases, this 1 or 2% increase in accuracy is very important, but it's not always the case. So right now, the use cases are dominated by industry because they can squeeze a lot of profit out of any advantage that they can get. I have a question in the chat. Is the drug discovery by quantum computing just an idea, or there are already real applications? There are already real applications. You can, if you look at some of the quantum computing companies, they're working with pharmaceutical companies on realizing these things. I encourage you to look at the Cleveland Clinic because they actually have a quantum computer on-prem. It's an IBM machine, and they're doing a lot of stuff in that direction. When you say no approximations, then quantum computing does not separate nuclear and electronic motion. I mean, you have to find a way to represent that motion on circuits, right? So that's really the trick is translating your problem again into circuits. If you are able to translate your problem in a way that does not separate, it contains all the correlations that you want, then yes. Um, you can do quantum computation with approximations as well. It doesn't have to be fully quantum. Okay, so we talked about some applications, we talked about algorithms, computation in general. We went over core concepts of quantum information science. Let's finally get to computers and supercomputers. So basically, building a quantum computer comes down to packing as many of these qubits as you can and implementing gates so you can manipulate them. There are multiple ways of doing them, as we talked about the physical support for building qubits before. In terms, when you talk about quantum computers, we talk about modalities. I can build quantum computers using superconducting circuits, trapped ions, neutral atoms, photonics, silicon spin, quantum dots. There are other modalities out there. Here are some players, industry players, startups, non-startups. Some of them are really big, like IBM and Google. Those are not startups, but and this is really just I'm not selecting this list for one reason or the other. There are many other companies that might be just if they're not here, doesn't mean that they're good or bad. It's just these are the ones that I put here. So let's go over some characteristics of these different modalities. Why does it matter? How are they built? What are why are there things that one is good for and the other one is not? I'm going to quickly go over this and try to show you some pictures of how these things look like, or what these things look like. The first one is the superconducting circuits. They're built using these engineered quantum components, linear inductors, Joseph junctions. In this type of computer, the gates are implemented by you're just like sending microwave photons to the qubits. Some of the pros of this way of building quantum computers, gates are really fast and they have good fidelities. That means that if I apply a gate, I know that this is exactly what the state's going to be. And you can do a lot of them in a short period of time. You can leverage some standard manufacturing processes, and they have some competitive advantage here because this is the first platform that was used, the first support that was used to build a quantum computer. So they've been in the market for longer. What are the cons of this modality? Well, it requires cryogenic cooling. These things have to be cooled down to microkelvin. So that's complicated. There's short coherence times, which means that my circuit is not the circuits that you can run on these things, it's not very deep, it's very shallow. And this thing is a little more technical, but basically, if you want to connect multiple of these things or connect them to other type of computers, the interconnects are not there yet. We have a comment here. I'll read that later because time is crunching here. Trapped ions. Here's an example of how what a trapped ion quantum computer looks like. It's fun. It's a lot of cables, huh? It's some of them really look like a physics experiment. Some of them are more advanced. People are starting to modularize them and be more engineered about, but some of them are pretty messy. So here you are using basically ions in free space, and you're controlling these ions using electromagnetic fields. An ion is a charged particle, so if you apply a magnetic field to a charged particle, you can move it around. The gates are implemented via lasers. Good things about it, really good gate fidelities, long coherence times, which means technically it allows you to have deeper circuits. Ions are perfect. They're particles. They're consistent. You don't need to cool it down to microkelvins. Gates on the con side, gates are actually kind of slow. So the whole thing about deeper circuits, not so much because if it takes too long for you to implement one gate, that means that it's going to take all of your coherence time. Um, Lasers are very difficult to align and scale. So if you look at this picture here, all of this stuff on this table here is just lasers and wave plates and mirrors and things like that. The actual ions are sitting in this tiny little corner here. Of course, they're small things. Neutral atoms. This one, it's also using atoms, but you can see that it's kind of like it's more streamlined. It looks more like a machine than just a physics experiment. Basically, also using similar to ion traps, also using electromagnetic fields and this things called optical tweezers. Um, Pros and cons. They also have long coherence times. They have strong connectivity, which means that operations between qubits, it's really efficient, even if these qubits are far from each other. No cryogenics required, and they can operate in analog mode. So far, we've been just talking about digital mode with those gates. Analog mode is very, very good for certain physics related problems. Um, you need ultra high vacuum for this. Scaling laser is also difficult, and that digital mode, which is the one that we were talking before, requires extra manipulation of these lasers. There are others, photonics, for instance. This is sort of like not as well developed. Very fast gates, no cryogenics, small footprint. Also can leverage existing fabrication process, but it can be very noisy. You can lose a lot of information because it's really hard to encode information on a photon and actually trap photons in this thing. Like particles of light are really difficult to trap. And they're relatively new, as I said, compared to others. The final one that I want to show is the quantum dots. I'm not really sure if this is actually a real picture or not, but it's from a Princeton University press release, so I trust them. Um, this one is very interesting because it's actually using semiconductors, which is pretty standard. It's a very well advanced industry. So there's some advantage there that you can use a lot of the existing manufacturing processes to build these things. But it also requires cryogenics, and you need to cool it down. Okay, noise, right? We talked a little bit about noise. We had questions about noise. So quantum objects in general, they're fragile. They're susceptible to error, noise sources. So for example, temperature fluctuations, coupling with the environment. You have this quantum system and you have all the environment around it. If you don't isolate this quantum system, it starts interacting with your environment and that disturbs your quantum system. There are coherent errors, meaning that I'm not going to go into details here, but like you have controlling imprecisions. Your gate might not be necessarily what you think that your gate might not be doing exactly what you think your gate's doing. And there are readout errors when you go to measure these things. There are hardware imperfections that can actually interfere whether you're going to measure a 0 or a 1. Basically, that is to say that these quantum computers are noisy. There are many sources of error for the computation. So that's why we people call that the NISQ era, the noisy intermediate scale quantum era. So that there's all the quantum computers these days, they're subject to noise. When you say long and short coherence times, what time scales are we looking for? Are we looking at? Depends on the platform, right? If you're looking at superconducting circuits, you're talking about microseconds. If you're looking at the trapped ions, you're talking about seconds. So if you look at each one of those companies, they'll have on their website, they'll have more details about that. So how do you handle errors? If there's so much noise here, how do you handle it? Well, and you know if you're going to use those quantum algorithms for something, you need to correct this error. You need to find a way to do fault tolerance like classical computers. So the cornerstone for to fixing these errors is what people call quantum error correction, right? So at a very high level, there are protocols that combine these qubits, these physical qubits, several of them into a logical unit, a set of qubits that represent a logical qubit, which is an error corrector qubit. So you account for all error sources and you fix them as you do computation. Here's one example. This is from Google Research. This paper was very impactful about a year ago, maybe more, 18 months. What they did is that they used the surface code approach to show that they can actually correct errors at a certain rate. Um, so you don't have to understand exactly how this works, but basically you have your data qubits that encode your quantum states, and you add measure qubits that you go and measure as you're doing computation, and these measures can indicate some errors. It's called a syndrome, and then you can fix that based on the syndrome that you're detecting. So it's all like, and that gets back to quantum classical workflows, because as you're measuring them, this becomes classical information that you need to read, interpret, and then go do something in your quantum space, depending on how you interpret this information. So there's a lot of back and forth between quantum and classical resources here. What the Google team showed basically is that you can correct errors in a rate that makes your logical qubit, in this case, more reliable than the physical qubit. So you're correcting error in a good rate. The problem with error correction is that this adds an overhead to your computation. There's all this back and forth, so it adds more operations to a certain, doing steps with a logical qubit, with a fault tolerant qubit, involves a lot of steps with a lot more steps with physical qubits. So whatever advantage you were getting with those algorithms before might be entirely wiped by this overhead of quantum error correction. So that's really the problem these days. It's finding quantum algorithms and finding quantum error correction algorithms such that your quantum speed up is not being wasted by your quantum error correction overhead. Uh, I see questions in the chat. I'm gonna get back to them in a little bit, but I want to talk about quantum supercomputers. So we can do after 1 p.m. Eastern for questions, but I need to talk about quantum supercomputers. So here's some examples of roadmaps of some of the companies. These are public. You can find them online. So for Google, for instance, you're talking about millions of physical qubits by, I think this is old. So it's saying we are here in 2023, but we're not in 2023, we're in 26. So you're talking about like millions and maybe tens of millions of physical qubits together. That doesn't mean logical qubits. If you see, this is continuous roadmap. They are projecting by 2029 about 100 logical qubits, thousands of physical qubits. Some others are more aggressive. This is IQM's. They're talking about thousands of logical qubits by 2033. Here's Square's roadmap. They're talking about 100 logical qubits this year. So you can check on their website, see where they are with their technologies. But we're still at the early stage of like having a small number of qubits, of logical qubits, error corrected qubits available for quantum computation. All right, so this is quantum computers in a nutshell. Let's talk about quantum supercomputers. How do we tie classical computing to quantum computing? So back to the helicopter example, quantum computers are really not general purpose. You're not going to use a quantum computer to do any sort of computation. There are specialized processors. There are co-processors. People sometimes call them accelerators. And they will likely be integrated into the high-performance computing environment with CPUs, GPUs, FPGAs, interconnects, and all of the other things that we have in classical computers, right? So you can think about them as some sort of workload accelerators. They will bring good advantage for certain workloads, but for other workloads, you will be way better off using CPUs or GPUs or whatever else. Here's one example how we can tie these things together, right? This is what some places already have. I think Oak Ridge National Laboratories, it's pretty close to either having this, if either they already have this or they're pretty close to have this. So they have their whole HPC infrastructure here, like thousands of CPU nodes, and they're all connected by an interconnect. And now they have in their data center a quantum system. Quantum system in this case, it's kind of alluding to a superconducting circuit based one. So there is a ton of stuff here. There's your control and vacuum system. You need your cryogen pump to cool the temperature down. You need a shielded room because these things are extremely fragile against any sort of noise, as we talked about. And then finally, inside these things, you got a QPU here. So it's a lot of, you can see there's a lot of layers for you to get from your CPU to your QPU. That translates into a lot of like overhead for hybrid quantum classical computation. In the future, as these things get more and more integrated into this ecosystem, you can think about different architectures. What it's also possible these days is to do these things for the cloud. So you have your standard HPC infrastructure, CPUs, GPUs, and then you have your quantum devices on the cloud. The advantage of that is that you can create a more dedicated environment, physical environment, where you can combine multiple quantum processors in a more controlled fashion. And you can even think about, if you have that type of environment, you can even think about building quantum interconnects. These are basically connections between your quantum processing units that can transmit quantum information. Here's the classical interconnect that can transmit um, classical information, but this is an active area of development, research and development, quantum interconnects. How do you communicate quantum information from one QPU to the other? As these things get more, that's the coupling and the integration here gets tighter and tighter. You can start thinking about bringing these things closer. Where, for instance, you have some sort of QPU that now has all the shielding in a more modularized and more efficient way, more well engineered way, and now it's sitting in your data center, and you have that tightly coupled via your interconnect to the CPUs. So these things are now exchanging classical information. There's no quantum interconnect here. They're not exchanging quantum information, but they're exchanging classical information very fast. And then for that, you can really do quantum error correction. Or you can think about a distributed way of doing this. Like this is pretty standard in HPC these days for CPUs and GPUs. You have multiple nodes. Each node has hundreds of CPU cores and dozens of GPUs, maybe not dozens, but 10, 8 GPUs is kind of the standard, 4 to 8 GPUs. So you can think about each one of your CPU nodes actually having a processing unit attached to it, and they communicate classically. As quantum networks get evolved, this is really sort of the ultimate architecture that is going to enable hybrid quantum classical computation at scale. So you have your CPUs and your GPUs. The GPUs are not detailed here, but trust me, people have CPUs and GPUs very tightly coupled together these days. So you can have your QPUs exchanging information with the CPUs classically, and they can have interconnects in between the QPUs to exchange quantum information in between the QPUs. This is really what gives you the most flexibility. Of course, for you to have all of this architecture of computing components working together, you need a stack that includes many things like software programming environments, resource and resource manager, workload managers, hypervisors, you name it, compilers. There's an entire ecosystem here. We've been talking really about the bottom of this stack here, talking about QPUs and CPUs and integrating them. But there is a ton of research, a ton of work to be done up the stack all the way to you actually can find the applications, right? So this is a very active area of development, research and development. And this is kind of like a high level overview of how you go from quantum algorithms to the quantum processing units. So you have to work across all these layers. There's a lot of work going on, different programming languages, a lot of work of people developing quantum compilers, thinking about architecture sets, thinking about microarchitecture, firmware, middleware, control electronics for these things. So it's very active field. So I'm going to stop here because it's 1 p.m. And thanks very much for your time. And I'll take questions now. Sorry for going over right at 1 p.m.
That's okay. There are some questions in the chat.
Yeah, I'll look at that right now. Okay, so I'm gonna comment. Does PSC have any research on qubits or just some theoretical studies? So PSC is a let me get the chat here so I can actually look at the screen. So PSC is a supercomputing center. We don't necessarily do research on qubits. That's really what folks at the physics department do, and some of these companies do. What we do is we turn computing technologies into computing resources for people to use, and we're trying to do that with quantum resources as well. So what we want to do is to have a quantum processor in our data center to integrate that with our standard HPC uh, um, equipment technologies. When you say long and short coherence times, I think I addressed that one. I'm interested in getting involved with quantum computing. Thanks. Yeah, please reach out. My email can be available. I can put my email in the chat if folks want to reach out, please. Um,
Thank you.
Way to reach out. And I think that's all the questions that I see.
Yeah. Are there any other questions?
Yes, I do have another question. It's there in the chat, but I'll ask again. So we talked about different ways of building the qubits and their pros and cons. Time scale of coherence is one of them. And so we talked about short time scale versus long time scale. I'm curious to know when we say short or when we say long, what is it that we are looking at? Like, is it microseconds?
Yeah, yeah. So that depends on the modality, well, how you're building these things. So for superconducting circuits, the time scales are microseconds. That's how, and the gates can actually be applied in nanoseconds. For some of the others, like trapped ions, the coherence time, which is basically the time that these things can maintain their quantum state without getting too much interference from the environment, you're talking about coherence times of seconds, but the gates can take milliseconds. So it really depends on the platform there. And then it's really about, coherence times, how well can you isolate your processing unit from external noise, and the ability to do very efficient or high fidelity gates. That's really what it boils down to.
Thank you. And there's just two more questions, and we'll wrap it up
Okay.
after that.
What type of companies are building these systems? Are they built in-house, or are contractors sharing information? It's a very active ecosystem. There are many startups. There are big technology companies like Google, IBM, Microsoft building their own computers as well. So it's all over the place. I'm not sure what you're referring to in-house, but there are many companies building these things in the United States, and there are many companies building these things in Europe, Asia, all over the place. Do we need general purpose applications available to everyone? So not necessarily. I mean, I think in the end, what this is going to look like is not long ago, people were still doing a lot of GPU programming, right? You have to do like, if you want to speed up your code and run it on the GPU, you have to adapt your code, your molecular dynamics code, to use the GPU. These days, there are libraries, everything, all the standard packages and applications are already accelerated. We're gonna get there at some point with quantum computing. People are going to develop these libraries. There's going to be a period of time where you're still going to have to put the work into porting your code to the quantum processing unit. But as these things mature, as the ecosystem evolves, this is probably going to look a lot more like GPU computing looks like these days.
We're going to need to wrap it up. I want to thank Bruno for starting with just the basics of quantum, who are leaders in the industry, to quantum supercomputers and interconnects and integration with classical systems that includes hybrid stack that's needed in the entire ecosystem. Thank you so much for sharing your expertise and your knowledge. And I'm going to pass it on to Emily to provide us with, what's coming next.
Sure. Thank you. Thank you, Bruno, for sharing that presentation. It was so interesting, and you really broke it down to the very base level as well. So it was very informative. For those who are still on the line, we do have a save the date for you. We have an upcoming event, which will be a quantum and generative AI career panel. So we'll have a few phenomenal panelists joining that event to speak a little bit about their pathways into this space and what they do today. That will be on April 24th, 2026. If you'd like to save that date, the best way to keep up with announcements for that is Florence dropped a link to our Quantum Initiative page in the chat. You can also directly sign up for our newsletter, where we will soon be announcing some more information about this specific panel. And then on the next slide, if you would like to connect with us, stay connected with us, you can join the Hub and NSDC newsletter through that QR code on the left. We have a LinkedIn and Slack account, Instagram, YouTube. We are also on Handshake and LinkedIn. And if you would like to connect with the ERN, the Ecosystem for Research Networking, you can do so through that QR code on the right. That will allow you to sign up for their mailing list. And you can also connect with them on LinkedIn. We also have our contact information at the bottom of this screen. So if you have any other questions or comments, feel free to email us and we'd be happy to get back to you. So again, we just wanted to say thank you. Thank you, Bruno. Thank you to the planning committee on today's call, Fru, Maureen, Florence. And then Fru, do you have any final parting words?
Well, thank you so much, everyone. And we'll look forward to seeing you on April 24th.